Hello everyone. Today we're going to present our work measuring feature quality for improved ranking performance in the SIGIR Ecom workshop. Learning to rank problem refers to the problem of finding the right rank of items for a given query QI. Typically, LTR dataset consists of a query, an item represented as a feature vector, and the relevant score of the item for the given query I. Some of the common evaluation metrics for learning to rank problem are mean average precision, NDCG, MRR, Kendall-Stowe, and so on. Metrics like NDCG at K, MRR, etc. are mostly output metrics, which only measures how well the model performs with respect to the given data. The metric lacks a general explainability as to what causes a drop or a change in the metric. It could be due to a poor model performance or a poor data quality. It is extremely difficult to root cause and diagnose a problem in real-world applications when there is a drop in metric like NDCG. This motivates us to propose a new additional metric called FICO or feature coverage. This metric is a simple metric that gives a wholesome view of the model performance in real-world ranking system. Now we'll discuss the metric. It involves a few steps to compute the metric. In the first step, we do data sampling. This is particularly relevant for real-world use cases. In this case, we have used systematic sampling, where we have sampled from 8-10 minutes window spread uniformly across a day. In the next step, we do feature selection. Ideally, FICO can be computed on all input feature. However, it is more intuitive to compute FICO on important features or user-centric user-centric features. In the next step, we compute the FICO score. Firstly, we determine our coverage threshold for the selected feature. This can be as simple as 0, where a non-zero value of the feature indicates that the feature has a meaningful contribution to model training. We can also consider the threshold to be a particular quantile value of the feature. Once a threshold is determined, we compute the sum of all the instances in our data set where the feature has value greater than the threshold of coverage. We divide this by the total number of samples in our data set. This gives a fraction of coverage, which we call FICO in this case. In order to get a stable metric, we compute a moving average of FICO score over a 7-day window. This is particularly relevant for real-world use cases where a feature can have a lot of drastic changes in between days. So having a moving average of the score helps in understanding the state of the feature. We'll now talk about the experiments in this study. We use two data sets. One is the publicly available MSLR Web 10K dataset, and then we also used an Amazon internal search data. We have used a GBDT model using the LightGBM library in both the cases. In order to find the baseline NDCG, we trained the GBDT model with the actual training data and tested it on the actual test data for both the data sets. We performed two experiments. In the first experiment, we trained the model with the original training data set and then tested it on the modified test data set. The test data set has been modified by altering the FICO score of some of the chosen features in the data set. In the second experiment, we have altered the FICO score of both the training data set as well as the test data set and trained the model and used it for testing. In all these cases, we have used the same configuration of the model and the same number of data set and the same number of training instances. We then observe the relationship between NDCG and the FICO drop based on the above experiments. We also plotted the feature importance curves with the original data set as well as the altered data set. Here we show the impact of the FICO drop on IndiCG matrix. In table 1, we show the FICO drop impact on IndiCG at 4 and IndiCG at 8 metric for the MSLR Web 10K dataset. The features have been renamed as column 15, 109, etc. For the feature column 15, we first dropped the coverage or the FICO score by 5% in the test data set. We observed the IndiCG at 4 to drop by 2.8% and the IndiCG at 8 to drop by 2.27%. We further dropped the FICO score of the same feature by 25% in the test data set and observed the IndiCG at 4 to reduce by 2.8% and IndiCG at 8 to reduce by 2.27%. We did similar thing with column 109 feature. There, a 5% drop in the FICO in the test data resulted in 3.16% drop in IndiCG at 4 and 1.92% drop in IndiCG at 8. On further dropping the FICO by 25%, we observed the IndiCG at 4 to drop by 3.34 and IndiCG at 8 to drop by 2.45%. We also altered the FICO score of the column 15 feature in the training as well as test dataset by 5% and observed the IndiCG at 4 to drop by 1.4% and IndiCG at 8 to drop by 0.87%. On further changing the FICO score by 25%, we observed the IndiCG at 4 to drop by 1.58 and IndiCG at 8 to drop by 0.69%. Similar study has been done on the Amazon dataset. We took the most important feature in our dataset and dropped the FICO score by 25% and observed the IndiCG drop of 2.23% for IndiCG at 4 and drop of 2.37% for IndiCG at 8. Same feature when undergoing a drop of 50% in the test dataset, observed IndiCG at 4 to drop by 4.8% and IndiCG at 8 to drop by 4.7%. We next picked another random feature and dropped the FICO by 25% in the test data, found the IndiCG to drop by 4.04% and IndiCG at 8 to drop by 3.29%. On further dropping the FICO coverage by 50%, we see further and stronger drop in IndiCG at 4 and IndiCG at 8 matrix. Moving on to the model explainability with FICO. We plotted the feature importance curve for the GBDT model using the original with respect to the original data set and then plotted the feature importance curve with the altered data set. In figure 1, we show the feature importance of the original data set. This is computed for MSLTR Web 10K data set. In figure 2, we show the impact of 5% drop in FICO score of the most important feature, which is called 267 in the data set. From the figure 2, we observe that a 5% drop in the coverage of the most important feature led the feature importance of that feature to drop. Similarly, additionally, we see that the FICO drop in this feature has led to the change in feature importance of the other features as well. This indicates that a FICO drop in important features may lead to a significant change in the model. Moving on to some of the applications of FICO in production system. FICO, when measured for engagement-based metrics, can help understand the extent of cold start problem in production. In the figure, we have shown the FICO score for a old and a new item. We see on tracking the metric over a period of time, we find that the new metric gradually gains coverage. The new item gradually gains coverage. At some point of time, the new item gains sufficient coverage to overcome the cold start problem. FICO of engagement-based metrics can also help understand the dynamics of customer engagement. This is typically important when a new service is launched in a particular location. In general, FICO can be used to monitor feature health in production system. It can be used in model explainability to root cause a change in model performance. Conclusion. In this study, we show that a simple metric like FICO can be highly efficient in evaluating the overall ranking performance. Our study shows that FICO has a strong correlation with output in the SIGIR metric. FICO also seems to have a strong impact on the feature importance in model training. We found that FICO has a wide applicability across different production level use cases. In future, we would like to study the impact of FICO and its applicability for other machine learning models beyond learning to rank. We would further like to unify FICO with output metrics like NDCG so that we can have a single metric that can give a full 360-degree view of the system. We would like to analyze and quantify the relation between FICO and NDCG metric. We would further like to analyze and quantify the impact of FICO on feature importance in models. Thanks everyone for your time.